Hi, so I thought today we should start to look at some other applications of the definite integral rather than just finding areas and volumes. Even though those are important, there are so many other things that integrals can do. So one thing that you've probably always wanted to know about is if you're on some type of curve, if you were riding along some function and you wanted to go from this point to this point, how far is that total distance? So maybe first if we were to look at like a curve y equals x squared, and you were going from x equals 0 to x equals 2. So from 0, 0 to 2, 4. What would be that distance? Well, if you just had to guess, would you pick 10? Where this is 1 unit, if you were going like from 0 to 1. I don't think that that would be a very good pick, because you can use some of your geometry knowledge. You don't need calculus to get an estimation. What could you do? You could say, you could go over 2 and up 4. That would be a total distance of 6, and you could see that that's less than 6. And then what other geometry knowledge do you know? You know the distance between 2 points on a straight line. So you could find that distance. It's just using Pythagorean theorem or the distance formula. So this side is 4, and this side is 2. So if you square 4, you get 16. Square that, you get 4. So this side would be the square root of 20, which if you put on your calculator, comes out to be about 4.47. So I think now we know the distance along this curve has to be between 4.47 and 6. We can make a pretty good estimate. Now if we wanted to do a little bit better than this straight line, what could we do? We could make Pythagorean's theorem twice. We could go from 0, 0 to 1, 1, and then from 1, 1 up to 2, 4. And I think you can see that that would be a better representation of y equals x squared. So there, now we've got 1, 1, so that would be the square root of 2 from here to here. And then this would be going over 1, and this would be going up 3. So this side would be the square root of 10. So if you add the square root of 2 to the square root of 10, you get about 4.58. So you can see you can start to come up with a pretty good estimate using geometry. But what if we wanted to get exact? I think you can see the more straight lines we have, the better. So you could do 100. You could break this up into 100, but then you're still not going to be exact. So let's go back over to here and see if we could do something where we split this up into more than 100. Maybe an infinite number of straight lines. So how could we do that? Well, first we could break it up into n. And let's just take a representative one, like we've done many times before, and we'll blow it up in size just so we can see what's happening. This is the kth subinterval right here, from xk minus 1 to xk. And we know this distance here we call delta x sub k. Well, if we went up to this point and this point, and we tried to figure out what this distance is from here to here, which is an estimate of this curve distance, we could say, we know this is delta x sub k, and associated with it, every point x sub k has a y sub k over here, so we could have a delta y sub k. And now, using the same distance formula, or Pythagorean's theorem, we can find out the length of that red line. What would it be? Be the square root of delta x sub k squared plus delta y sub k squared. And then what we could do to estimate this total length is to add up all n of these straight lines. So we would be adding up all of those straight lines. So we would go the square root of delta x sub k squared plus delta y sub k squared. And then we would sum them up from k equals 1 to n. But we're still going to have some error. So what are we going to do? We're going to take the limit as n approaches infinity. What we're going to do is make these straight lines basically turn into dots. And what we're going to be doing is adding up an infinite number of dots along here, and then we're going to have no error at all. Another magical thing we're doing with calculus. The trouble is, this is not an infinite Riemann sum. This looks right, and this looks right on all Riemann sums, but this is supposed to be what? We're supposed to have f of c sub k times delta x sub k. Well, one thing we could do is we can multiply by delta x sub k and then divide by delta x sub k. So we can put that where we wanted to, but now we've got to divide by delta x sub k. Well, we can do that by dividing under the radical by delta x sub k squared. Now, we're getting closer. This is going to be 1. And this is delta y sub k over delta x sub k squared. But now we have to go back to here. What do I know about delta y sub k over delta x sub k? That's the slope of this line. Well, the mean value theorem says there has to be some place between here and here where the instantaneous rate of change equals this average rate of change. So let's call that point c sub k. And that means this slope would be f prime of c sub k. So in place of delta y sub k over delta x sub k, we can put f prime of c sub k. And we still have this delta x sub k over here, and we have an infinite Riemann sum. This is a function of c sub k, and this is your delta x sub k. So now we've got what we wanted. We have an integral. Integral from where? From a to b of the square root of 1 plus f prime of x squared dx. And we've got a formula for finding the distance from here to here exactly. Now often, instead of writing f prime of x, you're going to see it written like this. The integral from a to b of the square root of 1 plus dy dx squared dx. Instead of f prime of x, if you write dy dx, it just makes it a little bit easier to see exactly what derivative you're taking. And I'll explain why, because there's sometimes, instead of taking dy dx, it might be simpler to take dx dy. Take the derivative of x with respect to y rather than the other way around. Without going through the whole thing, I can show you really quickly what you would do. instead of dividing here by delta x sub k, we could just divide by delta y sub k and multiply by delta y sub k. And the only difference is, now you get 1 here, and you'd have delta x sub k over delta y sub k squared. And that would turn out to be dx dy. You'd have the derivative with respect to y instead of with respect to x. So the other way you can write this, if this is c and this is d on the y-axis, you could write that the integral from c to d of the square root of 1 plus dx dy squared dy. So you have to decide what's easier to do, dy dx or dx dy. Now, there was a lot going on in here. So could we have made a mistake someplace? And the answer is always, that's a possibility. So what's one way to check to see if maybe this is right? We could try this out on something that we could really check. So what can we really check? We can check straight lines, because we know how to find that. So say we had y equals 2x, and you wanted to go from 1, 2 to 5, 10. Now we can find that with geometry. Let's see if we can find it with this formula. Well, we might as well take dy dx, because actually it's pretty easy both ways, but we've already got it solved for y. So we would be taking, by the formula that we just did, the integral from x equals 1 to x equals 5 of the square root of 1 plus dy dx, which in this case just happens to be 2. So we just have the square root of 5, and the antiderivative of the square root of 5 is the square root of 5x. And if we go from 1 to 5, we get the square root of 5 times 5 minus 1, or 4. That's what the formula would say. What would Pythagorean theorem or the distance formula say? This is 4, and from 2 to 10 is 8. So this side would be the square root of 8 squared plus 4 squared. You get the square root of 80. Well, 80 is 16 times 5, so you get 4 root 5. No, that's not a proof that our formula is right, but it gives us a good indication that we probably are. And now, let's just finish this one up. What is the distance from here to here? Well, dy dx is 2x. So we would take the integral from 0 to 2, because we're going in the x direction, the square root of 1 plus 2x squared dx. Or the integral from 0 to 2 of the square root of 1 plus 4x squared dx. So, the only unfortunate thing about this is we're not going to learn, even this year, until you get to Calc 2, how to do this type of integral. So for right now, we'll cheat a little bit and put it on our graphing calculator and let them take 10,000 rectangles to figure out what this is. And the estimation that the calculator gives is 4.65 when you actually do that integral. So you can see we were going from 4.47 to 4.58. 4.65 is just about perfect. So anyway, now you know how far it is along that curve. So let's just try a couple of examples using this that are a little bit more difficult. So say we want to find the length of the arc y equals x to the 3 halves. From 0, 0 to 5 root 5. So we know it goes something like this. And there's 0, 0. And there is 5, 5 root 5. So what's our first decision? Do we want to use dy dx or dx dy? It's already solved for y, so we might as well use dy dx. It's 3 halves x to the 1 half. So the formula says the length from here to here along the curve is the integral from 0 to 5 of the square root of 1 plus dy dx squared dx. So we put in there 3 halves x to the 1 half. So if I square it out, I get 1 plus, the square root squared is just x, so you get 9/4 x. Now, I'm not going to give up on this one like we did on the last one. We do have a method of doing this, but it's not perfectly in the form we want. So probably what we're going to do is do a u-substitution. We're going to let u equals 1 plus 9/4 x and du be 9/4 dx. So when I rewrite that, all this middle I can call u to the 1 half, and dx right here is going to be 4/9 du. And then I go from 0, but 0 is going to become 1, and then to 5. 5 is going to become 49/4. So if I take the antiderivative, of u to the 1 half, I get u to the 3 halves times 2/3. So altogether you get 8/27. Now you have to take the 3 halves power of this. So the square root would be 7 halves. And then you have to cube that. So you get 343/8 minus 1. Well, 1 is going to be 8/8. So we get 8/27 times 335/8. And the 8's cancel. And you get this, which is around 12. So the length from here to here is around 12 units, where 1 unit, again, would be the distance from 0 to 1 along the axis. Okay, so a different way to see if you could understand this formula, and also to test some of your skill from what we did in the last chapters, look at this problem, one like you've never seen before. If the distance along the curve y equals f of x, which they're not telling us what that curve is, from x equals 1 to x equals 3 pi over 7, is given by this integral. So they're telling us this time the distance along the curve in integral form. So we have to assume that they're using the formula, which means since this is dx, they must, this right here must be dy dx squared. Must equal sine of 2x squared. So what they've given us in these first three lines is they've given us what dy dx is in a sneaky kind of way. So now we know what dy dx is, can we figure out what y is? Well, this is solving this differential equation, and guess what else? They gave us a point on the function that we're looking for. So we've got a differential equation with an initial condition. We should be able to find out what the function is that we're looking for. So we take the antiderivative. The antiderivative of the sign is minus the cosine. Then we have to divide by 2 plus c. And now we use our initial condition that y is equal to 7 when x is equal to pi over 2. Well, that makes the cosine of pi, so a negative 1 times negative 1/2 plus c. So what does c have to equal? C has to equal 6.5. So that means y equals negative 1/2 the cosine of 2x plus 6.5. So now I can find out what y of pi over 6 is. The cosine of pi over 3 is 1/2, so I get negative 1/4 plus 6.5, or 6 1/4. So that one wasn't finding the length along the curve, but it was taking our knowledge of how to find the length along the curve to figure out what dy dx must have been, and then our knowledge of how to solve differential equations to find out what y is so that we could plug in pi over 6. So this is when you're really showing all your knowledge of calculus, or at least a lot of it. Okay, so let's end with one more. Find the length of this curve from 0 to 8. Well, I have a choice, dy dx or dx dy. This one isn't quite as obvious, but I think to solve for y is going to be a lot harder than to solve for x. So I think it might be better to say that x equals plus or minus y minus 1 to the 3/2. And since x is going from 0 to 8, and this I was always positive, we're rejecting the negative side. We're looking at the positive side of this curve. So now we know what dx is. So we're going to use dx dy instead of dy dx. So what is dx dy? It's 3/2 times y minus 1 to the 1/2. And then if you want to finish the chain rule, times 1, although that doesn't really do too much for you. And now we say the length is the integral of the square root of 1 plus, now I have to go dx dy. So it's 3/2 times y minus 1 to the 1/2. But now it's going to be dy. So I can't go from 0 to 8. Those are x values. So what do I have to do? I see when x is 0, if y minus 1 cubed has to be 0, y has to be 1. So where we're starting is when y is 1, and when x is 8, what squared gives you 64? This must be y minus 1 cubed has to equal 64. So 4 cubed equals 64, y must be 5. So we're going from 1 to 5 in the y direction. So let's see if we can solve this. The integral from 1 to 5 the square root of 1 plus 3/2 squared, and this squared is just going to be y minus 1. And altogether I get 9/4 y minus 9/4 plus 1 is minus 5/4. I think if we factored out a 1/4 out of here, it's really going to be 1/2 when you take it out of the square root. And you have the square root of 9y minus 5 dy. So I'm kind of getting you into a lot of old things in this because it really is good to review. It doesn't always work out perfectly. So now we have to do a u-substitution again. This is not y to the 1/2. It's 9y minus 5. So we let u equal 9y minus 5. du equals 9 dy. So if I rewrite this, I get the integral of the square root of, and this is going to be now just u. So it's u to the 1/2, and dy is equal to 1/9 du. And 1 becomes 4, and 5 becomes 40. So we're almost there, which is good because I'm running out of room. I get 1/18, and the antiderivative of u to the 1/2 is u to the 3/2 times 2/3. So that becomes 1/27, and you're going from 4 to 40. So you get 40 to the 3/2 power minus, and that's just going to be 8. And I think that's a number if you put that on your calculator. So pretty much we solved the real difficult one, and this one it was much better to go dx dy than dy dx. So that's one decision you're going to have to make on this kind of problems. So this was another example of what integrals can do. Tomorrow we'll get one that's even more valuable as far as the real world is concerned. So have a good rest of your day.